Welcome to Introduction to Multilateral Wells, Submodule 2 of 2. In this session, we'll build on the foundations from Submodule 1, focusing on the TAML levels of classification. We'll examine the features of each level from 1 through 6, compare them, and highlight how these classifications guide completion design and field development. The objectives of this module are to take the concepts we introduced previously and go deeper into the TAML classification scheme. We will explain the features of each level, from the simplest open-hole lateral through to the most advanced hydraulically isolated junctions. We'll compare the design elements that make each level distinct, such as whether the lateral is cased, whether the junction is mechanically supported, and whether hydraulic integrity can be maintained. Through this, you'll understand how junction integrity evolves from a low-cost, low-complexity design at level 1 to a high-cost, high-integrity design at level 6. We'll also look at summary comparisons, making it clear where each level fits in terms of accessibility, flow control, and re-entry potential. Finally, we'll review some alternative classification approaches used in the industry. By the end of this module, you'll be able to identify which TAML levels are suited for different reservoir and completion objectives and explain the trade-offs between cost, complexity, and functionality. Let's begin with Level 1. Level 1 represents the simplest form of multilateral junction. Here, the lateral is drilled as an open hole, branching from an open main bore, with no casing or mechanical support at the junction. The advantages are low cost and quick implementation. It enhances reservoir drainage by providing access to additional zones, but with minimal completion complexity. It is best suited to consolidated formations where borehole stability can be maintained without casing. The design allows multiple laterals to be drilled with relatively low capital expenditure, but the trade-off is limited lateral access after drilling. Once the well is completed, re-entering or intervening in the lateral is extremely difficult. Similarly, there is limited production control as inflow cannot be managed independently. The diagram on this slide shows a simple schematic with the main bore and an open lateral branching out. The absence of casing or support is clear, highlighting the simplicity but also the vulnerability of this design. Level 1 therefore offers cost savings but minimal control. Next, we step up in complexity to Level 2, where casing is introduced. Level 2 builds on the open hole concept by casing and cementing the main bore, while the lateral remains an open hole. This means the mother wellbore is stabilized and isolated, but the lateral junction is still unsupported. The key features include full main bore access. Because the casing provides structural integrity, we can still re-enter and operate in the main bore without difficulty. Another advantage is lateral re-entry potential, since the junction remains open and accessible from the cased bore. The cost is still relatively low compared to higher level multilaterals, but the design relies heavily on formation support at the junction. Without natural stability, the lateral can collapse or fail to produce long term. On the schematic shown here, you can see the cased and cemented mother bore with an open lateral branching from it. The contrast between the stabilized main well and the unsupported lateral illustrates the balance between integrity and simplicity. Level 2 is a practical option for consolidated reservoirs where intervention flexibility is required. From here, we'll progress to Level 3, where the lateral itself is cased. Level 3 introduces mechanical support at the junction. In this design, the lateral is cased and anchored back into the mother bore using a liner hanger. However, that hanger is not cemented in place. This setup provides a higher degree of stability compared to levels 1 and 2. Both the main bore and the lateral can be accessed, which improves operational flexibility. The junction itself is mechanically supported, reducing the risk of collapse. The advantages are clear. Intervention becomes easier, and re-entry into both bores is possible. Costs remain relatively low since the liner hanger avoids the expense of full cementing or pressure isolation. The limitation is that hydraulic integrity is not achieved. Fluids can still communicate across the junction. Looking at the diagram, you'll notice the lateral liner is fixed to the main bore with a hanger, but there is no cement barrier at the junction. This highlights the compromise: increased stability but without full zonal isolation. Level 3 offers a good balance for consolidated formations. Next, we'll see how cement in both bores further enhances junction support at level 4. Level 4 adds another layer of security. Both the main bore and the lateral are cased and cemented at the junction. This provides a mechanically robust and structurally stable connection between the two boreholes. The key feature here is that the junction is now supported by both tubulars and cement, greatly improving strength. This allows the design to be applied in both consolidated and unconsolidated formations, expanding its utility. Operators still retain full bore access to both the main bore and the lateral, so interventions remain possible. However, there is still no hydraulic integrity at the junction. That means fluid isolation is not complete. Formation fluids can still communicate across the connection. In the schematic on this slide, you'll see both the lateral and main bore represented with casing and cement around the junction. The presence of cement highlights how stability has improved compared to earlier levels. Level 4 is widely considered a practical compromise, greater security than open lateral designs, but less costly than the fully isolated systems. Next, we'll step into level 5, where hydraulic integrity is achieved. Level 5 represents a significant step up in functionality by providing hydraulic integrity at the junction. This means that the junction is sealed, allowing pressure control between the main bore and the lateral. The key feature is that pressure integrity is achieved through the completion design, not by cement. Cement is not acceptable in this case, as it cannot provide long-term pressure isolation at the junction. Instead, specialized completion equipment provides the seal. This level allows both main bore and lateral re-entry, making intervention and production management more flexible. It can be applied in both consolidated and unconsolidated formations, meaning it is suitable for a wide range of reservoirs. On the schematic, you'll notice casing through both the main bore and lateral, with the junction sealed using engineered equipment. The absence of cement at the junction is intentional, emphasizing the reliance on mechanical barriers for isolation. Level 5 designs are more costly, but they enable selective flow control and zonal isolation, vital for complex or high-value reservoirs. From here, we move to the most advanced classification, Level 6. Level 6 represents the highest standard of multilateral design. Here, both the main bore and the lateral are cased, and full pressure integrity at the junction is achieved using casing and engineered equipment. As with Level 5, cement is not acceptable because it cannot guarantee long-term hydraulic sealing. Instead, casing and specialized junction systems create a fully isolated connection. The key distinction is that Level 6 ensures full bore access to both the main bore and the lateral, while maintaining complete junction integrity. This is the only level where the junction performs with the same integrity as a conventional cased wellbore. It allows intervention, re-entry, selective production control, and long-term reservoir management. The system is suitable for both consolidated and unconsolidated formations, making it universally applicable. The schematic shows a fully cased and sealed junction, with clear pressure barriers between bores. This illustrates the robustness and complexity of the design. Level 6 is the gold standard for multilaterals, but also the most expensive and operationally challenging. To put all levels in perspective, let's now look at the summary slide. So let's bring together all 6 TAML levels and allows us to compare their features in detail. Think of it as a spectrum running from the simplest, lowest cost designs at level 1 to the most complex and fully functional designs at level 6. At level 1, we have an open hole lateral branching from an open hole main bore. This is the lowest cost option and can be effective in consolidated formations. However, it has significant limitations. Lateral access is minimal, intervention is nearly impossible, and there is no control over inflow. Essentially, it provides reservoir contact, but with little long-term flexibility. Level 2 improves stability by casing and cementing the main bore while leaving the lateral open. This allows full access to the main bore and the potential to re-enter the lateral. But again, the junction remains unsupported, relying heavily on natural formation stability. Level 3 introduces mechanical support at the junction by using a liner hanger to case the lateral back to the main bore. Both bores remain accessible, which improves operational options. However, hydraulic isolation is still not achieved. Level 4 cements both bores at the junction, creating a mechanically robust design suitable for unconsolidated formations. The major limitation remains the lack of pressure isolation across the junction. Level 5 changes the picture by introducing hydraulic integrity. Specialized completion equipment seals the junction, allowing independent control of the lateral and main bore. This makes selective production or injection possible, a significant advantage in complex reservoirs. Finally, Level 6 provides the highest standard. Both bores are cased, and the junction achieves full hydraulic integrity with engineered systems. This design offers complete re-entry, intervention flexibility, and pressure isolation, comparable to a conventional cased well. The trade-off is cost and complexity, but it delivers maximum reservoir management capability. This progression illustrates how engineers select the appropriate level based on reservoir complexity, cost tolerance, and production objectives. With this comparison in mind, let's look at how other classification systems evaluate multilaterals. While the TAML scheme is the most widely adopted way of classifying multilaterals, it is not the only system. Other frameworks exist, and these tend to focus less on junction integrity alone and more on practical aspects of how the well will be completed, accessed, and controlled. The first dimension is completion type. Here we can distinguish between single bore, dual bore, and concentric bore designs. A single bore completion uses one well bore to house both the main bore and lateral completion. This is the simplest but limits intervention options. A dual bore system provides independent completion strings for the main bore and lateral, allowing greater flexibility but with more hardware complexity. Concentric bore designs go further by running a smaller completion string inside a larger one, enabling both isolation and independent control within the same well. The second dimension is accessibility, how we can re-enter the main bore or lateral after completion. This is classified into three categories. NR, or non-selective re-entry, means we cannot choose which bore to access without major intervention. PR, or re-entry by pulling the completion, allows access but only after removing the completion assembly, costly and time-consuming. The most advanced is TR, or through tubing re-entry, where we can re-enter laterals using coiled tubing or wireline without disturbing the main completion. This is highly advantageous in terms of reducing downtime and intervention cost. The third and final dimension is flow control. At the lowest level, there is no control. Production flows naturally from all laterals. The next step up is SEL, or selective control, where we can open or close individual laterals to manage inflow. SEP, or separate control, allows completely independent production streams, often through dual completions. At the higher end, we have REM, remote monitoring, which provides data on lateral performance, and RMC, remote monitoring and control, where operators can actively adjust flow profiles in real time. Let's revisit the objectives of this submodule. We set out to deepen our understanding of the TAML classification system and the features that distinguish each level. First, we described the 6 levels in detail. We saw how Level 1 offers simplicity and low cost but minimal control, while Level 6 provides full hydraulic isolation and intervention capability at the highest cost and complexity. We compared the advantages and limitations of each design, focusing on completion type, accessibility, and flow control. This gave us a clear picture of how multilaterals can be tailored to different reservoir conditions. We also reviewed a summary of all levels, reinforcing how design complexity scales with performance. Finally, we introduced other classification approaches which, while less common, provide additional perspectives on design selection. By working through these topics, we've addressed all the original objectives, identifying key features, applying TAML levels, and understanding their implications for cost, control, and intervention. With that review complete, we'll formally close this submodule. That concludes submodule 2 of 2 on multilateral wells. You should now proceed to the quiz to confirm your understanding of the TAML levels and their applications. Thank you for your attention.